Hello, my friends. Today we are going to talk about electric potential. This is one of the subtopic under electrostatics. Suppose we have a point charge Q at this location. We are now going to bring an object from infinity to point A, and objects carry another charge, big Q, and we are going to bring this to there. So let's write this down here. Infinity, right? We are going to bring from infinity to point Q. So you may wonder how much energy will be required to implement this process. The answer is very easy. We better write everything down. Potential energy, and is given by a symbol U. Is given by the formula minus from infinity to x. X is where the point A is, and then the force, the Coulomb force, and then dl. And this formula is currently given in scalar form. So if you want it to be in vector form, it's also very easy. dl. So this will make sure you can sum up the contribution of potential energy at AFE point along the pathway. Now, what is force? What is the force here? The force is just the Coulomb force. We have already learned this. Is Q, small q, and then the big Q. 4 pi epsilon, and then L square in this scenario. So can we now use this Coulomb force formula to work out the potential energy? The answer is very easy. So we are going to derive it. Minus x and then infinity. And then the Coulomb force, right? Q and big Q. 4 pi epsilon L square dl. So this integral is expressed in scalar form. Now let's work this out. Minus, we have Q. We can bring all this constant outside the integral. L, and then L square and dl. And if you perform integration in this integral, you will end up with minus 1L and x infinity. So eventually what you will end up with is Q 4 pi epsilon, and you already learned that you have already learned the concept of electric field, and small q divided by 4 pi epsilon in this expression is just equal to E where E is the electric field radiated by small q, and then big Q. And then do not forget the have I done anything wrong? Yeah, I think I have done something wrong. Yeah, it should be like this, right? There shouldn't be any big E. Okay, yeah, it should be like this. This is good enough. Sorry about that. So this is the formula for potential energy. And the topic here is about electric potential. What is the relations between electric potential and potential energy? The answer is very simple. Electric potential refers electric potential is just the potential energy divided by Q. So this is the convention being used in electrical engineering. And normally we use the V to represent the electric potential. We use U to represent the electrical the potential energy. So in this scenario, according to this formula, the electric potential of 1 point charge is equals to Q 4 pi epsilon L. The big Q disappear because the whole formula is to divide big Q. Now we are going to apply this formula to find out the potential difference. Right now, what we have done here, I forgot to substitute L with X. What we have done here is the electric potential is to divide the formula for the electric potential at A. And in this scenario, the distance between the point charge and position A is X. So this is the formula for the electric potential at point A. Now, we are going to apply this formula to some other applications. Just remember this formula. Suppose we have we have a point charge. We are going to measure the electric field from one point. And the distance between the charge Q and this testing point is R1. And we are going to arrange another tester on another position, which is R2. So the question is, right, what is the potential between these 2 points? V21. So this is the variable we want to find out. And this is a very, very common question. we always need to know the potential between 2 points, either in the electric circuits or in any electrostatic applications. Now, let's work out the Coulomb force due to Q1. So Coulomb force, Coulomb's force due to Q1. F is equal to Q, and suppose you are having a big charge. The charge of your tester is 4 pi epsilon, and then the distance. Yeah, suppose we are measuring the distance, L. Like what we have done, we are going to find the potential difference between these 2 points. And according to what we have done just now, the potential difference between these 2 points to 1, the potential difference between between R1, the the reference potential at R1 is V1, for instance, is equals to Q1 4 pi epsilon R1. This is very important. Epsilon. And for exactly the same reason, we have also got V2 is equal to Q1 4 pi epsilon R2. So if you want to know the voltage between these 2 points, the easiest way to calculate them is just find the difference between them. So this is the voltage difference between these 2 points. One over R1 plus minus 1 over R2. So this is the voltage difference between these 2 points. Right now, this problem is not too common. It's common, but not as common as many people think. But I'm going to give you a more common example. But can we use this scenario to derive the voltage between 2 parallel plates? The answer is also very easy. What we can do is, in this case, let's write down the important result. In this case, we know that V21 is equal to Q divided by 4 pi epsilon, and then R1 minus R2. So this is the important finding. Yeah, what happened if R1 and R2 are both trending to infinity. What happened? So R1 is trending to infinity and R2 behave in the same manner. In this case, if you zoom in further, yeah, in this case, if R1 and R2 are both infinity, or you might just argue that, right? R1 is very similar to R2. And what happened, right? What is the scenario in this case? This means that if you zoom in this area, if you just zoom in this area, right? R1, both R1 and R2 are very similar. So we can just assume that R1 minus R2 is equal to the distance between two places. Where this d means that is equal to the separation between two parallel places. Parallel places. Yeah, because the R1 is infinity. If it is infinity, the curvature here will disappear. And if the outer sphere have the same problem, R1 become infinity, then we may assume the curvature at the outer sphere is also disappear. And in this case, you may assume these two shells, outermost shells and innermost shells, are just two parallel places, and the distance between these two shells is d, where d, in fact, is the separation between these two spheres. Or equally, yeah, we can also argue that, right, this is the separation between two parallel places. Now, in this case, I can rewrite the equation. We can rewrite equation 1. Rewrite 1. 1 will become 2, 1 equals to Q 4 pi epsilon, and then 1 over R1, and then minus 1 over R1 plus D, two parallel places. Now, if I'm going to explain the formula, I can say, let's work this out. This expression is going to Q 4 pi, and then we explain this expression. R1 plus D minus R1. And then the bottom expression is going to be R1 and then R1 plus D. Now, let's take a look here. R1 and minus R1 will cancel out with each other. So the top expression, the numerator here, will become D. Will become D. And how about the bottom expression here? R1 is very, very big. It's infinitely large. And D should be relatively small. So in this case, we may just assume, right? This is the approximate expression. R square, R1 square. And look, what happened now? You have D divided by R1 square. D divided by R1 square. And what is Q divided by 4 pi epsilon R1 square? It's just the electric field. ED. So we have worked out a very important relationship between two parallel plates. The voltage between two parallel plates is ED. So this is the so-called capacitor. So I can write this down, right? The voltage of a capacitor. Yeah, or I can just write down, right? So this is the formula for the capacitor.